let me give you a question first. So we've got a particle here. So here's our first example. Okay, so the avoid information.
I mean, I was actually asking for it. I was just saying, you just say.
I can just say it?
0, 0, and then highlight the information.
Okay, yeah, okay, so starts at 0, 0. So mass M. Initially, x is equal to 0, and the velocity is equal to v sub 0. This is all at initially.
And I guess it also takes the
The language.
Yeah.
Yeah.
Like terms you want to pull up.
Yeah, I agree. So a bit of both. I'll show. Why don't I? You can summarize it yourself, but read through the language, right? Crap. A particle of mass m, initial speed v sub 0, moves on a horizontal surface against a resistance, with resistance proportional to the square of the speed. So one thing that I didn't mention is when we talk about the resistive forces, because it's much easier to consider things without resistance. Like the problems that we get in the motion in extension 1, it's all without resistance, right? Like where would that be realistic? When would you have nothing, like no resistance really? Like probably not anywhere, right? There are things with very low resistance, like I don't know, like maglev train, or I've seen an experiment where they used like liquid nitrogen to imitate the maglev train, which is pretty cool. So there's no resistance with the surface. Maybe there's like some mild air resistance, something like that. But the idea is that we can have resistance in two ways. In extension 2, it will be proportional to its speed, so it's kind of like linear in that sense, right? And that's just kind of like, the faster you go, the more resistance you might experience. Right, like air resistance, for example. But then in some kind of substances, mediums, like fluids or when you're flying, right? In fact, it's not linear, but it varies proportional. It's roughly proportional to the square of the velocity. So one example they give for that is like turbulence, for example. That can kind of affect also not only the air resistance that you're experiencing, but the turbulence as well of the plane can create this effect here where it's proportional to the square. And that's exactly what's happening here, right? So we have this thing here, and it's mass m initially at the origin, moving at velocity of v sub 0. And because they tell you that it has a resistance proportional to the square of the speed, then you can actually create your equation. Remember, most of our equations will be relying on F equals to ma, right? So the force that this is experiencing, we say is negative because it's going in the opposite direction of our object. So if we have F is equal to ma, the force that we're experiencing is going to be, because they tell you it's proportional to the square of the speed, that's kv squared here, and the mass is just m, and acceleration we'll just leave there for now, okay? Now here's the key thing in determining which one of these forms of acceleration we want, right? If you want v in terms of x, well obviously you need something that relates those two together, right? And in fact this is going to be a key one that we'll be using a lot here. When you see v in terms of x, you'll want to use this one over here, v dv dx. If they want to relate the velocity and time, then we need to put those two together, right? So let's rewrite this in the form minus kv squared equals to m v dv dx. Remember, m is just like a constant, right? So it's not really doing anything over here, so we could just move it over. So minus k on m v squared, v dv dx. Now the idea is, what are we trying to find? We're going to try and find v in terms of x over here. But the issue is we don't have any x's here at the moment, right? So how can we sort of address this? Well, we've got two v variables over here, so we could put them onto the same side, right? And if you divide both sides by v squared, you would just get, what, 1 on v? What do you think we're going to do with these dv's and dx's over here? How can we sort of, quote unquote, get rid of them, so to speak, mathematically? Sorry, how can we sort of get rid of these dv dx's mathematically? Like, because this is just kind of sitting. Sorry? Integrate, right. And you remember there's a special type of integration that you did in extension 1 for differential equations. Separable, right? So where you can actually put the dx's and dv's on one side, It's kind of cheating in some sense, but we'll allow it for now. So that's dx is equal to 1 on v dv. And essentially, we're going to integrate both sides over here. Because the whole idea is you want v in terms of x. You can't really do that when you have these dx's and dv's over here, right? And so this becomes much more easily integratable now. So it's just minus kx on m is equal to, you know, what's this guy? This guy's just a ln. Now, another convention that occurs here, also we have, we have a constant here. Now, another convention is typically the problems that we have, the velocity is generally positive, or these expressions will be generally positive. It's not always going to be the case, but you'll notice in Cambridge, when you look through their solutions and things, they just kind of remove the absolute values. They actually just write brackets typically most of the time. So that's just something to be aware of in their problems that they do. Yeah, okay?
Well, what about the test?
It's a little bit tricky. I think a good practice is to leave the absolute values, but I sort of understand where they're coming from a practical side of things. Yeah, probably not, but I will double check for you. It's a good question. Let's get rid of it for now, and if we need to adjust it, we'll come back. Now, we actually do have some initial conditions, right? Because initially, it's at x is equal to 0, and v is equal to v sub 0, right? So we've got 0 is equal to ln of v sub 0 plus c. So c is equal to negative ln of v sub 0. Wait, did I do that right? Any mistakes there? I think that's right. Slightly different to what I had before, but it's okay.
This is v from 0, like, what is it just, like, what is the
It's the initial speed.
initial speed equal to?
It's just like another value for it. Yeah.
So speed's constant.
Yeah, v sub 0 is a constant, yeah. So this is initially. We
That
had
means that v is constant too.
v is not a constant. This is only initially.
No, but like,
yeah.
if it equals to v, which is constant.
As in, this is not always. This is just at t equals to 0.
Oh, okay.
Yeah. Because we need some initial conditions here to find the constant, right? So then once we get that, okay, and then we've got our c value. So then we haven't actually answered the question yet. So the question said we need to find v in terms of x. So let's go back to our original expression, which is over here. So minus kx on m equals to ln of v minus ln v sub 0. And then actually, this actually turns out quite nice because you want to make v the subject, but it's kind of locked into these logs at the moment, right? So we can actually use our log laws to bring them together. And then what's our next step, do you reckon?
Both sides of parity.
Yep, so raise both sides to the power e, so e to the minus kx on m equals to, well, using our exponential laws, is v on v sub 0. And so then v sub 0, v is going to equal to v sub 0 e to the minus kx on m. Yep. So that's our velocity in terms of x. So can you see how like all of these problems are going to involve like rearrangements, integration, and they may be kind of abstract like this one, or they may be applicable like the next one I'm about to give you. Okay.